Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have PSJ author Andrew Rivkin with us today. Hey, Andy.
Hi, thanks for having me.
Well, thank you so much for talking about your really lovely article on DART. And congratulations on the successful launch, by the way. That's very cool.
Thank you. Thank you. Yeah, it was great. It was great. We were out. It launched out of Vandenberg, so on the West Coast. A few of us actually got to go out and actually watch it. We had good weather, so.
Yeah, I was actually in Santa Barbara at the Kavli Institute for Theoretical Physics there. And so I sort of watched the launch from that area, and I watched it go up, and it was very cool. And it was, yes, awesome.
Yeah, I'd never seen a launch before. So first one, and it did not disappoint.
Very cool. Why Vandenberg as opposed to somewhere in Florida, let's say?
So my
West Coast.
So my understanding is that the inclination, the launch inclination, they wanted to launch south instead of more north-south instead of east-west. That's the way the mission design went. That's not my department, so to speak. So we were pretty early on. We knew that we were going to launch out of Vandenberg. So that had been in the works for a while.
Cool. Yeah, it was really great to see. Really great to see. And when you're not at Vandenberg watching launches of your missions, where are you located at, Andy?
I'm at the Johns Hopkins Applied Physics Laboratory, which is in Laurel, Maryland. So just about halfway between Baltimore and DC, and I live nearby. So that's where I'm calling you from, my kitchen table, my dining room table.
Well, I hope you have some coffee with it. So very good. So it is December 22nd, 2021 as we're shooting this, and we're about a day after solstice. So everybody enjoy your solstice celebrations. Any snow on the ground in Baltimore yet?
Snow, no. We've been pretty snow poor the last few years. There's been a few big ones, so we've been tending to get kind of 2 feet at a time when we get any. But so far pretty dry.
Okay, it's sort of the usual. I'm in Phoenix, Arizona. It's the usual Phoenix, lower 50s in the morning, and then we'll heat up to about 76 or so. It's pleasant as far as when winter goes. We got all those Canadian snowbirds coming down. So, all right. And Andy, what do you like to do for research in general?
So I study asteroids. I've been studying asteroids since graduate school. My dissertation was on infrared spectroscopy of asteroids, particularly in the kind of 3 micron region to look for hydrated minerals and organics and stuff. And that's been kind of my research direction ever since. Yeah, at some point on the way, being an asteroid person, you kind of naturally get involved in planetary defense questions.
Yeah,
well, a lot of us do. So that led to the involvement in the kind of studies that led to the DART mission. So now I'm one of the investigation leads for DART, which has been really something. First mission I've been on, so it's definitely been
cool.
a really learning experience.
Cool, very cool. And that is going to bring us to this very lovely Planetary Science Journal article. The double asteroid redirection test DART, planetary defense investigations and requirements, and we get to hear from lead author Andy and mission PI on this article. So Andy, take us away.
Sure. So I come out of a ground-based astronomy background. A lot of my observations, most of my observations were done from the RTF, and the kind of astronomy world is a different one from the mission world in a lot of ways. So one of the things we need to establish for the mission and for any mission is what does success look like? How do you tick the box that lets NASA or whomever say, yes, you did what you said you were going to do. This was a successful mission.
Cool.
So I'm sorry.
Then you get a second mission.
Well, one could at least cross their fingers. So So the DART mission has 4 level 1 requirements, top level requirements, that we need to achieve in order to be considered a success. And those are listed there in the abstract. We need to impact Dimorphos. So I don't know if I should back up, or if I guess I'll talk about this going forward. We need to hit our target, and we need to hit that target this coming fall. We didn't know the exact impact data at the time. We need to do a certain amount of deflection. We need to measure what we did to a certain precision, and then we need to interpret that in terms of how the change in momentum of the target is related to the amount of momentum that's brought in. The way that we're doing this here, and the reason that we're called the double asteroid redirection test, is that we're visiting a binary asteroid system. People have the planetary defense community has wanted to do. Actually, I guess I'll approach this a slightly different way. If something were incoming right now, and nothing is incoming right now, I will, we have to say this all the time, nothing is incoming that we know of right now. Yeah, there are a few different techniques that we think are ones that we might want to try to do something to address it, to deal with it. One is just civil defense, where you'd say just get in the basement, wait it out. There was an impact in Siberia in 2013 over the city of Chelyabinsk. If we had seen that coming, civil defense would have been what we would have done. We would have said, okay, it's going to be a flash at this time. You can watch the flash if you want, but then you've got 2 minutes to get away from the windows and,
bang.
Bang. The larger or largest impact would involve we probably, or the largest potential impact, we probably would use the largest tools in our toolbox, which is a nuclear device, and use those to do a standoff explosion and use the shock wave and vaporization to move things away. But those are for very big objects. And there are lots of reasons why we cannot and do not want to test that sort of thing. There are international laws and the like. So one of the other approaches that we think is technologically mature is what we call a kinetic impactor, which is basically taking your spacecraft or taking some mass and ramming it into the object you want to move, using the momentum that you bring in to change the velocity around the sun. And then that changes the orbit. And if you do it far enough in advance, then your object misses the Earth. So DART is one of those. Asteroids move around, orbit the sun at something like 30 kilometers a second. And we think we don't want to give a push of more than millimeters to centimeters per second in an object. We want to, asteroids are rubble piles by and large, or at least we think most of them are. And so the conventional wisdom is that you don't want to give a push that's or change the speed by more than the escape speed. The thing that of the object, of the asteroid, is that if you push it too hard, then you're going to disperse it. And if you disperse it, then you've got 24 things to keep track of, most of which are maybe still going to hit the Earth. So we think we want to keep these things intact. So changing the heliocentric speed of something by a few centimeters per second when it's going around the sun at 30 kilometers a second is very hard to measure. And that's kind of what stalled the original conceptions of this. So at the bottom of the section 1.1 there, we kind of talk about how we ended up, with the target we have and a little bit of history. The European Space Agency first proposed doing this. They wanted to do it with an asteroid orbiting the sun. It turns out that to make this measurement, you need 2 spacecraft. and they didn't want to pay for 2 spacecraft to make these measurements at this precision, which is, you know, not unreasonable for what the other things they had going on. So it was realized by my colleague Andy Cheng also at ATL that if you did this in a binary system and you impacted the moon of a binary system, and especially if it was an eclipsing binary, then you could just measure the light curve of the asteroid. You could measure the light curve before and after the impact, you know, and be able to determine the orbit period before and after the impact, and then pull out what you actually did. Cool. So that's the double asteroid part. Didymos itself is the target because when you kind of filter down, you know, there's a zillion asteroids out there, but once you start to say, okay, you need a binary asteroid, you need a binary asteroid that's eclipsing from the point of view of the Earth. You need a moon an asteroid moon that is of a size that you can appreciably, change its period. So it's got to be about this size. You want to do it at sometime soon and not wait 80 or 90 years for for your target to come by. And really, the Didymos system ended up being the only real choice we had. And then the moon of Didymos we named, or it was named Dimorphos, just about a little bit before this paper was published. There are other good reasons in addition to those kind of operational ones that Didymos makes a good target. The composition of the system is very much like ordinary chondrites, we believe, based on spectra of the large object Didymos. So we think that compositionally these are very much like the meteorites that most often hit the Earth. Ordinary chondrites, L and LL chondrites is to be even more specific. So we're not going to some weird, unrepresentative body. So what we'll learn about these objects, what we'll learn about moving these objects, will be applicable to a large fraction of what's actually out there.
Cool. Very nice.
Yeah. Okay. So then there, like as noted, and now just a bit more specifically is the level 1 requirements there. So what we need to do to be considered a success. So again, we need to impact the secondary member. Again, these were written before we even named Dimorphos. So impact Dimorphos, the secondary member of that system. We know we're going to impact now on the 26th of September Eastern time, the 27th of September UT.
Cool.
So so soon. We need to cause at least a 73-second change in the binary orbit period. Right now, the period is 11 hours and 55 minutes, something like that, 11.92 hours. We need to change it by at least 73 seconds. Okay. And then we need to measure, and then we need to measure that to 7.3 second precision. So that's kind of where we see the first two as being kind of the engineer's business. The engineers need to get us there. The engineers need to get us there with enough mass and momentum to make that change. Right. And then the rest of this is up to the scientists on the mission. We need to make these measurements to this precision. And then we need to understand, again, how the momentum change that's actually imparted relates to the momentum that was brought in, and why. So I'll get to this a bit more later, but this is not an 8th grade physics problem, because it's not a closed system. So so that momentum is conserved on a universal scale, but not on the scales that we necessarily care about.
It's a elastic collision.
Yep. So if we go forward a little bit, we can kind of skip. Well, I guess just to briefly touch on table one.
Yeah, sure.
You know, we are not a science mission per se. We're a planetary defense mission.
Got it.
And we, you know, we're not. We are administered from in NASA's Planetary Science Division, but we were not selected by a you know, a discovery mission call or a New Frontiers or like that. And so we do not, you know, just the names of positions, the names of things are a little different. So we don't have a science team. We have an investigation team. You know, that's why I'm an investigation lead, and you know, Nancy Chabot fills basically a project scientist role, but she is not called a project scientist because, again, we're not a science mission, but she is that. Yep. And then the team is broken up into various working groups, as you might imagine, and all of those groups have different roles to play in fulfilling these requirements. Mm-hmm. Yeah. As I said, requirements 1 and 2 are kind of the engineering team, more of the engineering team's. I guess I'll say responsibility. I don't know if that's quite the right word. Obviously, we have been purview. Yeah, we've been contributing as you know, as needed and as desired. The requirement number 1, and not requirement number 1. Requirement number 1 is, you know, we're going to go hit at this time, and it's that led to the investigation team needing to make measurements of Dimorphos so that the engineers would know where Dimorphos would be at the time we arrived. We're coming in at 6.5 kilometers a second. We are not sticking around. There's no rendezvous period. There's no anything. So we've got to hit. Yeah, we've got to come in and hit Dimorphos. Dimorphos is about the size of one of the pyramids of Egypt.
Okay.
Dart,
cool.
Yeah, Dart is about the size. People have been saying, I guess, a vending machine. I guess we've you know, kind of settled on a vending machine size with solar panels that stretch out to the length of a bus.
Yeah. And
we're coming in hot. So observations by the team, you know, kind of have been necessary so that we could say first, you know, okay, is Dimorphos going to be on this side of Didymos or this side of Didymos? Right. But now we've, you know, and as we got closer, you know, as launch got closer, those requirements got tighter and tighter. So now we think, or we have measured Dimorphos's period well enough that we can predict where it will be within just a few degrees of orbit phase at the time of arrival. So this plot here, figure 1, just shows something I mentioned before, kind of why we want to do this in 2022. This shows the distance from Earth on the y-axis versus date, and the Didymos system comes closer in this fall than it has come in a couple of decades, and as close as it will come in 40 years. You know, that 2003 apparition was an important one. We got really good radar measurements. That's when Dimorphos was discovered. But you can see that we kind of have, if we don't get Didymos this fall, then it's hard.
We have to wait.
Yeah, that was the time to do it.
Yep, very good.
Table 2 here just shows kind of our range of our range of what we kind of had to work with before we knew when we launched. Our launch period was very wide. We could have launched as late as February and still gotten to Dimorphos on time, but the arrival conditions changed considerably over that period. So we kind of had to work with a lot of possibilities. Right now, we know we're in that earliest column.
Okay.
So that's basically what we're looking at when we show up in terms of speed and angles. And then figure 2 shows just kind of shows graphically. I think this is for that first launch date, which is what we did. So this happily ended up being I think the appropriate one.
Oh, so you're coming almost head on. I mean, it's a little off angle, but more or less head on and round.
Yes. Yeah. That's the intention, is to come in head on. There's a couple of reasons we want to do that. That top left panel is, one of them is from the Earth. I think it's the top left.
Yeah, this one here.
Yeah, more or less. Or you can kind of get it from the others. Maybe the bottom left is from Earth. No, that's from dark. Oh, from Earth is bottom right.
Oh yeah.
So
different angles.
If we want to hit,
yeah,
we want to hit close to head on, because if we want to cause the most, so we want to hit or have DART hit Dimorphos as close to head on as we can. We want to basically get the incoming velocity vector lined up as close as we can with Dimorphos's orbit vector to cause the greatest deflection. Dimorphos is only moving something like 20 to 30 centimeters per second or less. So compared to the incoming speed, it's really tiny. So it doesn't necessarily matter that much if we hit head on or 180 degrees later. But we don't want to hit it 90 degrees off, because then you're not really doing too much good. The reason that we want to hit it head on, 2 reasons. One is kind of a convenience thing. The orbit period is 11.92 hours. Like I said, if we hit it on the other side, the opposite of head on, then we would make the orbit a little bit bigger and the orbit period a little bit longer.
Right.
And it would be inconvenient to make it 12.00 hours. We could work with it, but it would be inconvenient. So this is going to make the orbit period smaller. That also binds it a little closer to Didymos, and some people get concerned about all sorts of things. So being able to say, no, we will not detach Dimorphos under any circumstances. I mean, not that we would do that, but right, that people, okay, we're binding it a little closer. And then the lighting also is better. We have the chance potentially to see the unlit side of Dimorphos lit by Didymos shine.
Okay.
If we hit it head on.
Yeah.
And also if it goes into shadow, if we were to hit it on the opposite side, then it would be go into eclipse from Earth not too long afterward, and then we would not have communication. And so we just want to make sure that we can communicate that we have a line of sight to Dimorphos for as long as we can during and after the impact.
Cool.
So so that's that figure. Observations are really important, as noted. DART is a very unusual mission in that much to most of the important data will be taken after the spacecraft is destroyed. So we're going to be making these measurements from Earth. That's really important. The next figure shows the observability of the system from the Earth. So this shows the solar elongation and the V magnitude. The shaded regions are where the elongation is less than, I think it's the solar elongation is less than, is greater than 90 degrees from the sun.
Yeah.
So so that on the top panel there, it shows both where it's bright enough and where it's far enough away from the sun. The solid line shows the it shows September 30th, 2022. So it's not the actual impact date, but it's just a few days later.
Yep.
So you can see that basically we're going to observe it pretty close to at least at the brightest.
Yeah.
And it should be plenty bright. You know, I know this is a AAS, AAS Journal, a AAS podcast. People are used to seeing their Q equals, or their Z equals 50 quasars at, 28th magnitude or something. But this is good because we can get lots of telescopes, lots of observers around the world, even with very modest apertures. We'll be able to take data that would be potentially useful for us.
So let me go there. Is there an opportunity for citizen science here on that?
Yes, there's an opportunity for citizen science. We are trying to be. We've got a lot of plates spinning, or balls in the air, whichever vaudeville metaphor you prefer.
Right.
So we are going to just focus on kind of getting the data that is required to do the measurements we need, and we're not going to have a lot of time or resources to vet other data.
Right. Sure.
Vet citizen science data, but people should be able, certainly I think should be able, even with very, very modest telescopes, to see the light curve change. Cool. We have actually, I guess that's a great segue into this next piece, because we talk about the kind of what we are going to need to make the measurements to the precision that we need so I guess I'll finish this thought and then I'll circle back to figure 4, which is the next figure. But basically, what we need to make these measurements from our simulations is data with a signal to noise of 100 or so.
Okay. Mm-hmm.
At a cadence of an image every 2 to 3 minutes.
Okay.
The mutual events, so the times when Morphos is moving in front of Didymos and casting a shadow, and moving behind Didymos and being blocked, those are effects of a few percent in the light curve. So we want to be able to have a secure measurement of those drops. We need to have they last sort of a half hour or so in duration. So we need to have a multiple a multi-sigma detection of those drops with several points across the duration, and we get information from the shape of the light curve. So
yes.
So that's what we think we need for the data we need to take.
Mm-hmm.
Having said that, again, citizen scientists, people with that cannot meet that threshold, still might be able to make observations for just to see if they can do it. Still be able to see, maybe instead of a 4 sigma drop and 10 points across the mutual event, they get 2 or 3 points, they get whatever. That's great.
That's great. Super.
Yeah. So we think we have this requirement to cause a 73-second change in the orbit period. We think it's probably going to be more like a 10-minute change.
Ooh, okay.
We think we've got plenty.
Wow.
73 seconds was based on it was an observational kind of constraint or guess or estimate. Basically, we figured that if we changed the orbit such that it was kind of led to a 10% change in orbit phase relative to prior to impact, and we let that accrue over a month, that would lead, you would need a 73-second change to have that happen. Just from, here's the spacecraft we have, here's how fast we're going. Again, we think we're going to get a much bigger change than that.
Well, that'd be great. Very cool.
Yeah. Figure 4 just shows the observability from the telescopes that we're planning to use. We have supported team members who have telescopes in Chile, in the southwestern United States.
Mhm.
We expect to use telescopes on Hawaii. So these show that Didymos starts out in the southern sky. It's very well placed for southern hemisphere observatories, including Chile, but basically anything at that latitude, which is Australia, South Africa, all of that. Didymos then starts to move north after, I guess a little before the impact, but then in the weeks after the impact, it becomes very well placed for the northern hemisphere observatories.
Okay.
Mauna Kea, but then again, southwestern United States, the Canary Islands is not on here, but also is kind of in one of those northern hemisphere observatories. And basically, it stays observable for a good part of the night, up until the point when it gets faint enough that we don't think we can get the precision we need at the cadence we need, which is going to be sometime in kind of late winter, early spring 2023.
Yes.
So the next figure is a bit. I'm second guessing the colors for it, but I'm a little colorblind, and at least I can see the difference between these colors in Figure 5. So this is kind of a schematic, better than a cartoon, but not much, that kind of shows what these mutual events from the system look like. And again, they're about 0.8 of a magnitude. They last half hour or so. In the unperturbed case, you had got that black line, and this is again just kind of notional. If we do the minimum change and wait, I think this is 15 orbits, so about a week.
Okay.
Then these mutual events will occur offset from the unperturbed case by some amount. That should be easily measurable. And again, if we think we cause more like a 7-minute period change, we expect, then they're going to be offset by hours. So we will make measurements of the new period, from scratch, treating it like, without bootstrapping.
Right.
But we do think that this means that we'll be able to at least come up with a pretty good idea of what we did pretty soon after the impact. Once we start to be able to say, okay, if we didn't hit it, there would have been an impact. There would have been a mutual event at 2 o'clock, and instead we're seeing it at 12:30.
Right.
So that means that this is what happened.
Okay.
Most of what we do is going to be with optical telescopes. We do have Hubble Space Telescope time that's been granted to us.
Nice.
We do have James Webb time. Didymos is moving. Yes, of course. Fingers crossed.
You did.
For all sorts of reasons. But Didymos is going to be moving faster than the James Webb spec. But we've been working with them to kind of work around that and see what we can do. And then there are some other facilities that we're hoping we'll be able to use. Radar is one of them. Of course, we're mourning Arecibo.
Yes.
But the Goldstone radar, we expect to still be operating, and we expect to get some good data from them. And they will be an independent measurement in addition to the optical measurements. So we think we can, potentially get a very rapid sense of what we did within a few days.
Yeah.
Potentially.
Very cool.
So moving on to this last requirement. So we're looking at this parameter called beta, which is the momentum transfer efficiency.
Uh-huh.
And again, so here you've got kind of three choices. The A branch there is you have an inelastic collision, everything is conserved, beta equals 1, the momentum change is equal to the momentum you bring in.
Yep.
But we do expect to make a mess. We do expect to throw off some debris. That debris carries momentum with it. And that will give a push, an extra push. It'll be the equivalent of giving it an extra push. We don't know if that is going to be more like a 20% effect, or more like a factor of 2 or a factor of 3. There are reasons for thinking it could be either of those. If we hit something that's a rubble pile, the porosity will take up a lot of the energy, and so that will lower beta. If we hit something that's more like solid rock, then there will be a lot of fast-moving ejecta, and that will drive it beta higher. But then what also matters is whether you have rubble piles or rocks on the scale of the spacecraft.
Yes.
So you could have a rubble pile, but if the rubble pile is made up of 20-meter boulders, then as far as the impact is concerned, you have a solid rock. And so, so that is going to be, this is where the measurements made from the spacecraft itself come in, and impact simulations by the folks in our team that do that. So we have one instrument on board DART, which is a camera called Draco, which is the Didymos Reconnaissance and Asteroid Camera for OpNav.
Nice.
And you can see a picture, figure 7 shows kind of an example of the highest required resolution. This is of course the asteroid Itokawa, which is about twice the size of Dimorphos. So this is the required resolution. So chop Itokawa in half here, and you get a sense of what we might get for Dimorphos that's required. We will continue to take images all the way in and send them back as fast as possible until they can no longer be sent back.
Yep.
So the required resolution is 50 centimeters per pixel or better. We expect to get hopefully 3 times that, maybe a little better. Maybe get down to I don't think we will get millimeters per pixel. I don't think anyone expects that at all. I think it's going to be a few to 10 centimeters per pixel, or maybe 10 to 20 centimeters per pixel. But again, this is going to be obviously really useful for us. We need to build a shape model for Dimorphos to get its volume. We need to make estimates of its mass, which I'll get to in momentarily here. And we also need to understand the impact site. Did we hit a boulder? Did we hit an area that's more gravelly?
What's the cadence of the camera and the ability to shoot that data out before impact? So how quickly does that turn over?
The camera has 2 modes, as I understand it. Either it is off, or it is taking images at 1 hertz. So it takes an image every second.
Okay, I'm with you.
Yep. And it's a CMOS detector, so it's not a framing camera. So it's gonna, send stuff off without going to. It doesn't get saved and then sent out. It just gets sent out. I think I forget the exact numbers, unfortunately, but it is sending it out at a rate such that most but not all of the images will get sent down. I mean, just in general, the software, or the I guess not the software, the system basically says, what's the next picture, and sends it. You know, what's the newest picture, and sends it out. And that takes a bit longer than a second. So
Okay.
some things, if they are not the newest picture, might get exposed. But then if something else shows up before it gets sent out, the new picture gets sent out, the slightly older one gets thrown out.
Okay.
So we can't necessarily predict what that means in terms of which images get sent down, but certainly it does mean that the last picture will get sent down.
Okay.
Yeah.
Whatever that is.
Yeah.
Yes.
Yes.
Okay. Thanks.
Yeah. So
Yes.
going on to the mass estimate, understanding the momentum transfer requires us to have some idea of what the mass of Dimorphos is. We are not going to measure. We are not going to measure the mass because we're coming in too fast. We're just not going to do that. We have a mass for the main body for Didymos, and so we have a density for that. And then we're basically using various arguments for what the density of Dimorphos has to be to then get a useful mass. So this is in table 4. On the way down to table 4, I think you'll pass figure 8, which just shows how well we think we'll be able to model the shape of Dimorphos from our images. And now here's table 4, basically shows the different approaches at this point that we would have for estimating the density for Dimorphos, and then the uncertainties.
Okay.
And basically we think it more or less has to be, we have some decent upper limits. We have some looser lower limits. At this point, we're going to go in probably with that top one and assume it's the same density as the main body. With then an understanding of what we might learn on the way in that might change those. And there is a European mission that will visit the system a few years after DART. European mission called Hera that will make more precise measurements of the mass for Dimorphos, and will allow us to kind of go post facto and
no, it's valuable. Nice.
And figure that out.
I did not know that.
So we have these inputs to beta, and if you back up a little bit to section 5.3, we've got an actual equation that I'm not gonna walk through, but I will at least touch on. So we developed this value for beta, for the momentum transfer efficiency, based on what's observable. What different data sets are going to give us. The velocity of the spacecraft, for instance, is going to come from the engineers. The mass is going to come from one of these estimates. The mass of Dimorphos is going to come from one of these estimates. The angle of the angle relative to the surface normal is going to come from the imagery of the surface. The period change, the delta V, is going to come from the astronomical observations. And sort of separating all of these out so that there are specific data sets that we know are going to go into giving us that beta number that we decide upon, that we agree upon, and also to do the error propagation appropriately.
Cool. Yep. Good.
And then at least I think the last thing I'll mention here, in section 6.2, we talk about ejecta specifically. So we don't know how much ejecta we will make, and therefore we certainly do not want to hang any sort of success or failure on
How much?
that sort of thing. When we mostly this is a right, mostly this is a planetary defense demonstration, and
Correct.
so if we can show that we can move move this asteroid, we don't want to get someone hung up with like, well, you said you were going to measure this, and so
right.
But on the other hand, we will make ejecta, almost certainly. And so there is an opportunity there. The DART mission is carrying a CubeSat from the Italian Space Agency called LiCiQ.
Nice.
And that CubeSat, this is Italy's first deep space mission, actually. So they've been part of course, numerous ESA missions. But this is the first one by the Italian Space Agency itself. So it has 2 cameras. It's going to be deployed about 10 days ahead of the DART arrival.
Okay.
And it will follow DART. It's going to maneuver so that it does not hit Didymos or Dimorphos. And then it's going to image the DART impact. It's going to make its closest flyby about 3 minutes, I think, after the DART impact. And if we can get imagery of the impact ejecta, then the specifics of the ejecta plume will give us information about the surface properties of Dimorphos.
Yes.
And then hopefully, I don't know. I'm old enough to remember that Comet Kohoutek was a thing, even if I'm too young to have been personally affected by it. So we would like to be able to say that people, again, will be able to go to their local planetariums and, hey, maybe we'll make a plume that you can see from the ground. Maybe we'll make a tail. That would be great. We have no idea, really. Dimorphos has to cooperate. But if so, we'll have people that are observing, again, to watch the ejecta evolution and be able to use that to kind of give constraints on the size of the impact crater that we make and the like.
Cool. Very nice.
Yeah. So that's the main. That's kind of our main summary here. In Appendix A, we include everything we kind of know and agreed upon on the mission for what Didymos and Dimorphos are like. Kind of the data sets that go into them, what we are using for the sizes of the bodies, for the rotation periods, and all of that, and then their where they were derived. This appendix is already a little bit out of date. We have some follow-up papers that are going to include some better numbers for the orbit period of Dimorphos, for instance. Yeah, this is kind of, we're excited to share what we did and what we're going to do, and be as transparent and inclusive as we can with what we're doing.
That is totally awesome. And there's Appendix B, in case you're really interested in how beta was derived, that expression.
That's right.
Beta, you can go through it there.
That's right. That's right. And shout out to Tom Statler and Steve Chesley, who did most of the grunt work in Appendix B there.
There we go. All right. Andy, I want to thank you once again for walking us through your really lovely PSJ article and the launch. So you touched on it a little bit at a couple of points as we go through. So what do we do, let's say, over the next 8 months or so as we sit on pins and needles waiting for the main show? So where do we go in the short-term future with DART?
Yeah, so DART right now, in case anyone is interested, at the moment I'm speaking, it's up in the constellation Hercules. Okay. It's about 96 hundredths of an AU from the sun. It's about 4 hundredths of an AU from the Earth, and it's about 125 degrees solar elongation from here. It's going to stay in a very Earth-like orbit. And Didymos comes by as we talked about one of those figures. Didymos makes a very close approach to Earth. This
Mhm.
Fall, so DART just mostly just kind of hangs out and waits for Didymos to show up. We are, yeah, we're doing, there's a lot of technology that we are testing on this mission as part of the kind of, can we do this, you know, what, not only are there the science investigations, but the engineering tests and technology tests.
Oh, yeah.
All of those are going well. There's this rollout solar arrays that have been deployed very soon after launch, and those work well.
Awesome.
And we are, you know, testing out the camera, calibrating the camera, and then we wait. The Draco camera doesn't detect Didymos until about a month out.
Okay.
So that'll be sort of late August. It'll detect it in long exposures, and then it'll appear as a point, getting brighter and brighter very slowly. About 8 hours out, we turn over the steering wheel to the smart nav algorithm
Okay.
to bring us in. It'll appear again, just still as a point for most of the way in. I think it's not until the last, you know, hour or so that it looks like a couple of points, and it's not until the last few minutes that Dimorphos itself gets to be, you know, kind of an appreciable thing. So a lot of excitement.
Yeah.
In those last minutes, and until then, we're just preparing and getting our telescope proposals ready and making sure, you know, that we touch base with Didymos and it's still acting the way we expect it to. So,
And all systems are go.
All systems are go.
Awesome. That is great. Andy, I really look forward to a lot of really exciting news coming up here in 8 months or so. It'll be super, and I hope it goes really well.
Thank you.
Cross fingers. And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.